So in section 7.4, we're going to try and find a confidence interval for a population standard deviation or a population variance, so sigma or sigma squared. In doing that, we're going to need to work with a new distribution, and that new distribution is called a chi-square distribution. So yet another Greek letter for us, chi-square distribution. Kind of like the t-table or the t-distribution, that distribution is going to change with degrees of freedom. So to kind of keep an eye on things with the chi-square distribution, this is a chi-square distribution with 1 degree of freedom, 2 degrees of freedom, 3, 4, 5, 6, or actually, I guess it goes 6 and then 9, 6 and then 9, etc. So the shape of the distribution, like I said, changes with degrees of freedom, and I'll give you a little bit more of a live demonstration than just the one we have there. So let's go all the way back to n equals 3 for a chi-square distribution and just let it roll. So here we go. So as you change the degrees of freedom, what happens? It starts to look more and more symmetric. In fact, what's another thing that you might say about this when the degrees of freedom increases? What is this one starting to look like? Yeah, it's starting to look like a normal distribution. And for larger and larger degrees of freedom, it does have a normal appearance. So a few of the fun facts we should know about the chi-square distribution. Actually, we don't need to know all of them, but certainly the first one that's true about all our distributions is that the total area is 1. Total area underneath that curve is 1. It's not symmetric, so that's unlike our t distribution and our z distribution. Those are both symmetric. In fact, this one doesn't even go below 0. So it starts at 0 and then increases from there. Like the t distribution, it changes with degrees of freedom. And after a while, it starts to have a normal look. Now, a couple bonus things that I'm not sure you'll find in the book. One of them is that the mean of this distribution is the same as its degrees of freedom, and its variance is 2 times the degrees of freedom. So not something that you need to know, but it's there nonetheless. You can kind of appreciate that when you look back at our little video here. Let me start back at the beginning. As you increase from 3 degrees of freedom all the way up, the distribution starts to spread out because there's more variance. And as it increases, like I said, it becomes more and more normal. So now, one of the challenges that we're going to be faced with is finding critical values from this distribution. So we're going to need to find areas in the right and left tail. We'll do that 2 different ways. First, we'll do it old school with the tables, and then we'll do it new school with stat disk, and we'll see what you like best. So let's see, for our first one, let's try and find the value of the chi-square distribution with, say, 2.5% of the area in the right tail for 11 degrees of freedom. So, for example, chi-square sub 0.025 with 11 degrees of freedom. If we're going to do this with a table, then open up to the appropriate table. I believe it's on page 728. Look down for degrees of freedom. Degrees of freedom is 11. And then we want the area to the right of the critical value. So we want that area to be 0.025. So slide over till you're underneath 0.025. What number are you finding for this particular chi-square distribution? Yeah, I'm getting 21.920 as well. So 21.920. Now sometimes we need the chi-square value from the left portion of the tail. So kind of following along with our previous example, if I want the chi-square value that puts 2.5% of the area in the left tail, how much is going to be in the right tail? 97.5%. So 0.975 is what you're going to look for in the table, because the table is going to give you the portion of the area that's in the right tail. So sticking with this same degrees of freedom, chi-square, 11 degrees of freedom, 97.5% of the area in the right tail. Now I get a chi-square value of 3.816. So chi-square sub 0.975 of 11 degrees of freedom was 3.816. So that's using the table. And we can use a table, that's fine. Nothing wrong with that. But, using the table gets a little bit prone to error. So let's try it with technology. Let's see it with StatDisk. So if you open up StatDisk, let's go over to Analysis. And the first thing underneath Analysis that you see is probability distributions. So go down to there. Probability distributions. And then you want the chi-square distribution. So Analysis, probability distributions, then chi-square distribution. Everyone got this one? When you click it, you get something like this. So there's a couple different ways you can use this table. Degrees of freedom, let's do the same example that we just did. Degrees of freedom was 11. You can do one of two things. You can say, all right, I'll give you the area that I want to the right of a particular point, and then you give me the chi-square value. So in our first example, we wanted 0.225 of the area to the right. And you can click Evaluate, and there you go, 21.920071. So we even get a couple bonus digits compared to what the table gave us in the book. You could work this the other way too. Suppose you have a chi-square value and you're like, well, gee, what's the area associated with that? So the other one that we did was we found 3.816. So you could type in the chi-square value and say, okay, well, how much of the area is to the right of that point? Now when I click Evaluate, what should I get? Approximately. About 0.975. So, how come it's not evaluating? Okay, there we go. Yeah, it's not putting it here. It's putting it here. Thank you. All right, so the area to the right is something that would round to 0.975. Okay, so nice. I like using technology to find these things. If you want to use the tables to find these things, that's great. Now, one thing about using the chi-square distribution as part of our work in trying to find a confidence interval is that it's no longer going to be a nice symmetric interval. If you think back to the work that we did with the t distribution and the z distribution, we're trying to find confidence intervals based off of those. It was always x bar minus an error, and x bar plus an error, or p hat minus something, p hat plus something, but they were symmetric. You had your point estimate, which was your x bar or your p hat. Those were your point estimates, surrounded by a little wiggle room, a little room for error. But that's not true of our chi-square distribution. For our chi-square distribution, here's our confidence interval. So said for chi-squared, actually for sigma squared, or for our variance, here's your confidence interval. Now, one thing to keep in mind is that there's kind of a little disconnect here. You're going to take n minus 1 times your sample variance and divide it by chi-squared sub r. Chi-squared sub r is in the right tail, whereas chi-squared sub l is in the left tail. Now, if you then want a formula, or excuse me, a confidence interval for the standard deviation, you can take the square root of all three parts of this inequality and get this one over here. The good news for us is that unless you want to do this by hand, which you can, we can do this with technology. So we're going to apply this first of all to problem number 6 and see how things go there. I think I'm going to start out right away just doing it with stat disk. To me, it makes sense. These calculations are things that, you know, are a little bit annoying and sometimes difficult. So we're going to do it with stat disk. Okay, so problem number 6. Just kind of a nice bread and butter problem. Says we want to find a 99% confidence interval for the standard deviation of the weight of dollar coins. So let me write down the relevant information that we're given here. 99% confidence interval. N equals 40. S is 0.0411. It's 20. Oh, thank you. N is 20. 0.04111 grams. Okay. Now, one of the assumptions, and I'll go over this a little bit more when we start doing our hypothesis test for the same parameter. One of the assumptions is that you have a normal distribution and a simple random sample from that normal distribution. That's a pretty hard assumption in this one. With our work with the mean, and to maybe a little bit lesser extent with our population proportions, if it's not perfectly a normal distribution, etc., then it's not critical, just as long as you have a decent sample size. But here, the assumption that you have a normal distribution is important. And later today, when we work on hypothesis testing, we will spend some time on that assumption. We can check it now. For now, let's try and find our 90% confidence interval. So we'll go back to stat disk. Analysis is going to get a lot of work done for us. Any suggestions where I want to go down from here? I think confidence intervals looks pretty good. Confidence interval for standard deviation, 1 sample. So let's click that. What level of confidence do we want for our interval? 99. So let's change that. 0.99. Sample size, Chris helped us out with that. That was 20. And the standard deviation was 0.4111. So with all that, let's hit the magic button here. The nice thing in doing it this way is that you don't actually have to go finding the chi-square value yourself, nor do you have to do lots of tricky arithmetic. It's all here for you. It's all nicely laid out. So here's your confidence interval for the variance. So between 0.00, let's see. Yeah, let me go with the one up here. Let's go with the confidence interval for the standard deviation. So 0.02888 or 8849 is less than the standard deviation, and that's less than 0.0684, etc. 968. I'm not going to make you copy down all these numbers. I'll say, all right, just round it to the nearest 10,000th, etc. for an exam. Now, the nice thing, like I said about the technology here, is that, boy, it's doing a lot of work for us. That's going to allow us to concentrate a little bit more on interpreting this stuff, which is really the job of a statistician, is to come up with the interpretation. What's this mean? So one thing you want to avoid in talking about confidence intervals and their conclusions is saying the word probability. There's no probability associated with this anymore other than a 0 or a 1. It either contains this population parameter or it doesn't. We don't know which. The procedure will work 99% of the time if our assumptions are met, but we don't know if this is the 1% or not. But we can be pretty confident in it. We can be 99% confident that the true population standard deviation pardon me if I'm getting a little bit lazy here, pop standard deviation of the weights of coins, weights of dollar coins, is between 0.0288 and 0.0685 grams. And that's it. There's your confidence interval for the population standard deviation. They also gave output for a confidence interval for the population variance, which is just the square of all these numbers. The problem with using the variance is that it's not on the same units as our original data. Our original data is in grams. The variance would be in grams squared, which doesn't seem to make a whole lot of sense. So it made more sense to me to use population standard deviation. Okay, how are we looking on number 6? Comfortable with that one? All right. Let's try a different one then. Problem number 20. Or we could do one where we actually have to put in some of the data ourselves. Want to do one that's a little bit more interactive? Yeah, okay. Let's try problem number 16 then. Okay. So for problem number 16, we're just going to do part A. We've got some waiting times for Jefferson Valley Bank. Their waiting times were 6.5 minutes, 6.6 minutes, 6.7 minutes, 7.1 minutes, 7.3 minutes, 7.4 minutes, and then 3 at 7.7 minutes. So that's our data set. We're going to input that into StatDisk and try and come up with a 95% confidence interval for the population standard deviation. So let me switch over to StatDisk and enter that data. So I can get rid of this. I'm just going to put it in column 1. So if you want to follow along, 6.5, and then 6.6, 6.7, 7.1. Did I miss a 6.8 in here? All right. Yeah, I did miss a 6.8. I'll have to add that to data, so 6.8. The order that you have these in is not going to matter, so we should have 6.5, 6.6, 6.7, 6.8, then 7.1, 7.3, 7.4, and then 7.7 3 times. Okay, so we have 10 data values here. One thing we could do is kind of look at our data really quickly, try and decide if it looks like it is normal. I'll be more demanding of this in the next section, but if you click Data and then go down to Explore Data with Descriptive Statistics, then we can do that. Our data is in column 1. If you hit Evaluate, well, we don't have a whole lot of data. That really doesn't look much like a normal distribution. The normal quantile plot doesn't look as bad, except for, well, these at the end, those 3 7.7s are not so good. But there's a procedure that we'll look at later on when we understand more about the p-value that'll help us out. For now, let's do our confidence interval. So go back to Analysis, down to Confidence Interval, and then over to Standard Deviation 1 Sample. This time, instead of using the summary statistics like we did with the previous one, we're going to use data. So let's click Use Data. 95% confidence level, we're okay there. It's going to look in column 1, so wow, great. Evaluate. Nice. So there's your standard, or there's your confidence interval for the standard deviation. 0.32, call it 79, is less than sigma is less than 0.8702. What I want you to do is take a minute and try and write the conclusion for this. Now keep in mind that the parameter we were estimating was a standard deviation of waiting times for Jefferson Valley Bank. So try and write that conclusion in words. This is going to be a big and important part of your grade for these things, because you don't have to do a whole lot of arithmetic anymore. It's just interpreting these things. So that's where the emphasis is. can use our first one as a model. Okay. Darlene, what'd you get? How should we phrase it? Perfect. Perfect. Mine's just a little bit different, but it's more or less the same thing. We can be 95% confident that the true standard deviation of waiting times is between these two numbers, and the units, of course, would be minutes. So some of the things that I'll be looking for is that you use the word confident, like you did. Another thing that I want to see is you describing in words this parameter. So that's the true standard deviation. That's your population parameter. It's not the test statistic. So don't use S here. S would be your sample variance or sample standard deviation, not the population standard deviation. So perfect. Well done. Thank you. Okay. Are you comfortable with this procedure? Comfortable with these things? Especially what they're doing with the stat disk part? Tad? Yeah, okay. All right. Let me give some homework then. For homework, try 1 and then 5 through 15. That should do well.